Good morning, everybody. Mr. Lake here with another chemistry instructional video. Now, for the last couple of weeks, we've been really focusing on the structure of atoms, what subatomic particles are there, and how they relate to one another. And you've been introduced to this concept of a stable versus an unstable nucleus or nuclei. And today we're going to dive into a little bit more of what that means and how it relates to something that you've probably heard a lot about throughout your life, which is radioactivity. So, first of all, you've probably all heard of radiation, something you're supposed to stay away from and limit your exposure to, right? And there are a lot of things that radiate, but when we talk about radiation as in the, harmful bad one that can cause mutations or cause cancer or cause other diseases or things like that. What we're really talking about is ionizing radiation, which is certain types of energies or certain types of matter that can interact with molecules in our body and cause damage and cause change. Specifically, we're really concerned about our DNA, right? If something can interact with our DNA and cause change, that means that it can cause a mutation. It can cause a harmful mutation. It can cause a gene to break down so that it doesn't work, so that cells don't function properly. And then we end up with problems because of that. There is a small chance that it also results in a beneficial mutation or a nonsense mutation, something that doesn't really matter. But we're really, concerned about how many of these mutations we allow to happen in our bodies because of the fact that they could potentially be harmful to us. But again, what is radiation, right? You hear it talked about all the time. You see it in movies. People use, those Geiger counter things that, like, when you point at something that's radioactive, it goes from like, right? Spot on impression there. Um, what is the Geiger counter measuring? Like, what are those little clicks or beeps or whatever? And why do they become more frequent when you point it at something that is radioactive? What does that mean? Let's dive into it. Let's answer that question that you've maybe had for a long time. So it goes back to the nucleus and that concept of stable versus unstable. So a stable nucleus is a nucleus that is not going to spontaneously change. It's like a very solid, well built nucleus without any issues. However, there is the possibility for a nucleus to not be stable and for it to be unstable, in fact. And when the nucleus of an atom is unstable, what that means is, well, it means the same thing as any other stable or unstable structure, is that it's probably going to fall apart, right? Like, look at this shipping container here, or this ship with shipping containers on it. These things were stacked really, really high, not the most stable structure that could have been built. And when the ship kind of got jostled, or it looks like it maybe ran aground on a reef or something like that, um, and the ship tilted to the side, what happened to that unstable structure? It fell over, and probably some pieces fell off of it, and those pieces are probably sitting at the bottom of the ocean right now. Well, an unstable nucleus is also going to fall apart. It essentially means that that nucleus has a expiration date. And when that expiration date arrives, it's going to fall apart and something is going to fall off of it. But when we're talking about nuclear decay, which is another name for this, when that thing falls off, it doesn't really fall off, it more like fires out of it at high speeds. So, to cover some terminology, a nuclear reaction, which I'm sure you've heard that term before, a nuclear reaction is very simply a reaction that involves an atom's nucleus. Nuclear, nucleus. Makes sense. When this happens, it emits radiation. The nucleus, generally, when this happens, it's because the nucleus is unstable and it falls apart. and something is going to fall off of it, and we call that thing that falls off of it radiation. And something that is undergoing this process is called radioactive. Because remember that when you have like a sample of something, you don't just have one atom, you probably have billions of atoms. And all of those billions of atoms are going to go through this process of decay at different times, kind of just depending on where they're at. And so that chunk of, a radioactive substance, it's not just going to have one moment where it releases all of its radiation. Those atoms within it are going to be, releasing radiation at different times. And so that chunk of material is probably going to be radioactive for a long time. There's, we're going to get into the nitty gritty here. And the first thing that we're going to talk about is, well, there's three different kinds of radioactive decay that we're going to talk about. The first one is called alpha decay. Now, we talked about alpha particles briefly in the last video with regards to the Rutherford experiment and how alpha particles were used in that experiment to detect the nucleus. Well, it turns out that alpha particles are a result of nuclear decay of the nucleus. So it's very poetic that they were used to discover the nucleus in the first place. And what alpha decay is when an unstable nucleus kind of shifts and falls apart, and the piece that falls off is consisted of two protons and two neutrons. That very specific arrangement is called an alpha particle. So the alpha particle can't be anything different than that. It can't be like three protons and two neutrons or one proton and one neutron. An alpha particle is specifically two protons and two neutrons. Now, and what happens to this alpha particle is that when it falls off of the nucleus, it fires out of the nucleus at high speed, and it's going to, go in some random direction, and it's going to eventually hit something. And that is what we are concerned about when we are in the presence of radioactive decay, because if that alpha particle hits us and hits our DNA, it could cause a harmful mutation. If it hits another atom, another nucleus, it can cause a change. Alpha particles, are potentially, they're kind of like little atomic bullets, and they can cause change or they can cause destruction depending on where they land. But it's also important to think about what the implications of that are for the nucleus, the thing that just fell apart. How did that atom just change when it lost two protons and two neutrons? So take a look at this example down here. We're going to look at the example of uranium 234, which is a uranium atom, and all uranium atoms have 92 protons. And it's specifically the isotope uranium 234, meaning that its mass number is 234. When this thing loses two protons and two neutrons, that means, first and foremost, its atomic number is going to decrease. It just lost two protons, which means it's actually going to change into a different element because it's the number of protons that determines what element we're dealing with. So if it loses two protons, its atomic number decreases to 90. By the way, this arrow just means like this is a reaction arrow saying that this thing on the left is going to turn into this stuff on the right, right? That we'll cover this more in the future, but the stuff on the left is called the reactants. The stuff on the right is called the products, are called the products. So when it decreases from an atomic number of 92 to 90, that changes it to an atom of thorium. Because thorium is number 90 on the periodic table. That's the element with 90 protons. So it just changed into a different element. In addition, it also lost two neutrons, which means that between the two protons and two neutrons, that's going to decrease the mass number by 4. So the mass number goes down by 4, in this case from 234 to 230. And over here, we have a representation of the alpha particle. Now, this might be a little bit confusing because this says that this is an element of helium or an atom of helium. Let's think about this. There's kind of two ways to represent or to write an alpha particle. The first and easiest way that I use the most is just the alpha symbol, which is like a backwards fish. that means alpha. And if you write that, like if we had just written thorium plus alpha, that to me represents that the thorium is, or sorry, the uranium is decaying into this version of thorium. And in the process, it's also giving off an alpha particle. But there's another way to write an alpha particle because it is something that consists of two protons and two neutrons. What else consists of protons and neutrons? The nucleus of atoms. So, really, what's going on here is that a very tiny nucleus has been created. And since it has two protons, that's a nucleus of a helium atom. And since it has two neutrons and two protons, it has a mass number of 4. So, another way you can write an alpha particle is with this symbol right here that's been shown. That essentially an alpha particle is a helium atom with an atomic number of 2 and a mass number of 4. Now, the thing that makes it different than probably most helium atoms you would just go out and find in nature is that it doesn't have any electrons. It is only the nucleus. But still, it is the nucleus of a helium atom. So you can represent an alpha particle with just an alpha symbol or with this um, element symbol here. It doesn't matter so much to me. You should be able to read it both ways. You should be able to write it both ways. So I would recommend practicing it both ways. Now, these can be kind of tough. So let's do an example. I'm going to stop talking for about 5 seconds, and I'd like you to pause the video and do your best to write the equation for the decay of radium 226. Pause the video and start it once you have your best try. Okay, I hope you gave this a try. Let's look at the answer. First of all, we have to write an element symbol for radium 226. Now, how we're going to do that is we're going to use the symbol for radium, and to the left of it, we're going to write the mass number, which is given to us. It's 226. And we're going to write the atomic number. Where do we get this? From the periodic table. So we had to look up radium on the periodic table and find out that it is number 88. Now, when it goes through alpha decay, it's going to give off an alpha particle. And here's an example of how to write this in this format, not the helium format. Radium is going to go through alpha decay. It's going to give off an alpha particle. And this thing, remember, has a mass number of 4 and an atomic number of 2. So that means it's going to decrease the atomic number by 2 from 88 to 86, which changes this element from radium to radon, which sound very similar, but they are actually very different elements. And the mass number goes from 226 down to 222. It loses 4. Hopefully you practice this. Hopefully this makes some sense. If it doesn't make sense, make sure to ask me questions during class because this is something that you're going to be expected to do on worksheets and assignments and quizzes in the future. I am expecting you to kind of understand and be able to write out alpha decay. Now, there's one other type of decay that I'm also expecting you to be familiar with and be able to write out, and that is beta decay. The beta decay is very, very different. It's also a type of radiation, and it does also emit a particle, but it emits a very different particle, which of course is called a beta particle. A beta particle is just an electron. That's it. A beta particle is very simply an electron. So when something goes through beta decay, and the Greek symbol for beta is this right here, which you can kind of write by just writing a B, but make the bottom of the B extra long. So instead of this, just extend it a little bit further. Right? You might think, oh, okay, well, it's just losing an electron, so that's not going to affect the nucleus at all. The element's not going to change into a different element or anything like that. But actually, you would be a little bit wrong. In fact, what happens when beta decay happens is that the atomic number increases by 1. The mass number stays the same. So here's an example, carbon 14 going through beta decay, it goes from carbon with an atomic number of 6 and it turns into nitrogen with an atomic number of 7, but the mass number doesn't change. And at the same time, an electron is given off. But remember, this is a nuclear reaction. It's happening in the nucleus. Are electrons in the nucleus? No, it's only protons and neutrons. So, where in the world is this beta particle, this electron, coming from in the nucleus if there's no electrons in the nucleus? And how is losing an electron increasing the number of protons by 1? What is happening here? Well, okay, let me explain. When something goes through beta decay, what's actually happening is that a neutron decays into a proton and an electron. Remember way back when we talked about how neutrons are a little bit bigger than protons? It actually turns out that a neutron is, roughly, not exactly, but it's roughly the mass of a proton and an electron put together. Because that's kind of what it is, which makes sense because it has a neutral charge and a proton has a positive and an electron has a negative charge. And if you were to smash those two things together, the positive and negative would cancel out and you get something that's neutral. And so a neutron has the ability to decay into a proton and an electron. Like that electron can sort of just fall off of the neutron. And since that negative charge is leaving the neutron is left as a positive charge and it just becomes a proton. And that's what's going on here. You've got a neutron decaying into a proton, which is why the atomic number goes up because you just gained a proton, but the mass number stays the same because between protons and neutrons, there's the same number. It's just that you had one switch to another one, right? You had a neutron switch to a proton. That's not going to change the number of protons and neutrons because you just exchanged one for one, but the number of protons goes up. And the element moves up on the periodic table and it goes up one to the next element. At the same time, that electron that was created, there's suddenly an electron in the nucleus. Do electrons belong in the nucleus? Not at all. And so it's going to get like kicked out of the nucleus at high speed and it's going to shoot off. And that is the particle that's given off in this case. Hopefully that made some sense. Now, something you're going to be expected to do is you're going to be expected to write the decay equation for something going through beta decay as well, and be able to kind of keep it separate from alpha decay and be able to do, one or the other depending on the situation. So let's practice that. Let's write the beta decay of lead 214. I'm going to stop talking for 5 seconds, pause the video, try this on your own, and hit play when you have something. Okay, hopefully you gave this a shot. Here is the answer. Let me walk you through it. If we find lead on the periodic table, we'll find that it has kind of an interesting abbreviation, PB. You'd think it'd be like L or LE or something like that, but it's PB. And that goes back to kind of the Latin roots of it. We don't have to get into it right now. It is sort of interesting. Um, Originally, lead was, well, I guess I'm going to get into it. Originally, lead was called plumbum. And so that's where the PB came from. And then at some point in English, it changed from plumbum to lead. The atomic number of lead is 82. We found that on the periodic table. And we were given the mass number, which is 214. So this is how we're going to write the lead atomic symbol that's going to decay. Now, when it decays, in beta decay, the atomic number goes up. So it's going to go up to 83. That is going to change it to bismuth, which is the element with the atomic number of 83 on the periodic table. And the mass number does not change because a neutron just switched to a proton. Now, here you'll notice that there's also a secondary way to write a beta particle. I'm not such a fan of this. I mean, you can do that if you want, but let's just go ahead and replace this. Let's try and keep things simple with the beta symbol. So, to review, what's happening in this reaction is that the nucleus of a lead 214 atom is decaying into bismuth 214 that has an atomic number of 83, and a beta particle is produced and flies off of the nucleus at super high speeds. Pew! Action sound effects. Now, there is a third type of radiation that I'd like to talk to you about, but the good news is that this doesn't involve any equations. It's not a different like type of equation that you need to be able to write or anything like that. Really, you just in this class, we're going to focus on alpha and beta decay, and I'd like you to be able to write equations for both of those so that you really kind of get a fundamental understanding of what's going on in some of the most common types of radioactive decay. However, I would be remiss if I didn't also mention gamma rays, which are a very common type of radiation. You've probably heard of gamma rays before. Maybe you've watched any number of the Marvel movies in the Marvel Cinematic Universe, and you're familiar with the Hulk character. And of course, the Hulk character was created by exposure to gamma rays. Bruce Banner was exposed to, and I might be getting this wrong, and I apologize if I am, but if I remember correctly, the lore is that Bruce Banner, a scientist, was exposed to a high amount of gamma rays, and it mutated his cells, and it made him into something that could temporarily from time to time turn into a big green creature that said, Hulk smash! And smashed things. But then he would turn back. Scientifically, it doesn't make any sense, but gamma rays do actually exist. They are a real thing, and they are basically just high energy radiation, high energy rays. Gamma rays are in the same spectrum as other electromagnetic radiation. So, visual light, light that you can see, microwaves, infrared, ultraviolet, and gamma rays, they're actually all the same type of energy. It just depends on what frequency and what wavelength they are at that determines where they fall on that spectrum. So essentially, when atoms fall apart in radioactive decay, sometimes they just give off energy. They don't actually give off a particle. And oftentimes that energy is a gamma ray, which is basically just a super, super high energy light ray, since it's on the same spectrum as that. Um, and even though this doesn't have any mass, it's not an actual particle, gamma rays can also produce mutations. If you're exposed to a lot of them, they can mutate your DNA. So there is some truth to that part of the Hulk story, although the actual mutation that Bruce Banner got, pretty unlikely. Now, it's also important to note that sometimes gamma decay or gamma radiation emission does accompany alpha or beta decay. So let's do an example to partially just get another practice run at alpha decay and also partially to show how you might write when alpha decay, how you might write it when alpha decay is accompanied by gamma decay. So I'm going to stop talking. I'm going to disappear for a moment, pause the video for pause the video. I'm going to wait for 5 seconds, turn the video back on when you have attempted this. All right, here it is. Let's start at the beginning. And by the way, I don't think I went over with you how to write gamma. That probably would have been helpful for me to do. The gamma uh, symbol is what you're seeing here. It's very similar to the alpha symbol, except you're going to write the fish swimming down, right? And technically, like, you kind of want to write it like that, but this is fine. This is fine. So if uranium 238 is going through alpha decay, first of all, we have to confirm what the atomic number of of uranium is. We've got to get out our periodic table, look this up. Its atomic number is 92. We're told that the mass number is 238. So here's how we're going to write the atomic symbol to begin with on the left. Then we write an arrow saying this is going to decay into the stuff on the right. Remember, an alpha particle is something with two protons and two neutrons, so an atomic number of two and a mass number of four. Here we're representing it by the alpha particle. I like that very much. And when this thing falls off of the nucleus, it means that the nucleus is going to decrease by these same amounts, right? So the bottom number, the atomic number, is going to decrease by 2 down to 90. And the top number, the mass number, is going to decrease by 4. It's going to go down to 234, which means we now have a new element. Thorium is number 90 on the periodic table, and that has a new mass number. And then in addition, this reaction releases gamma radiation. So we're going to write the gamma symbol over here saying, in addition to this, it also releases some additional energy. I don't expect you to know when something does or doesn't release gamma radiation. So basically, for the purposes of this class, which is an introductory chemistry class, if I tell you that something releases gamma radiation, that means I'd like you to write it in the equation. If I don't mention gamma radiation, you don't have to assume or you don't have to figure out that it releases gamma radiation. You don't have to include that. All right. We're not going to get too into the weeds on when things release gamma radiation or not. That's a little beyond the scope of this class. So there you have it. There you have it. That is um, the required part of the video. And I know the video is quite long already. So if you need to, for your own sanity, turn things off, you can do that. But I do want to kind of go over a little bit more information for those who are interested about the discovery of these different particles and some of the things that we know about them. So, what you see below is a depiction of an experiment, and you might notice that there's some similarities to the setup of this experiment, similar to the Rutherford experiment that we talked about. Um, this was an experiment intended to determine the charges and the masses of the different radioactive particles. So, if you have a radioactive source that goes through alpha and beta particle decay, and we'll talk about how that is possible, how something could be going through both, or how something could go through both throughout its lifetime. We're going to talk about that in just a minute. But let's say you have a sample that is going to release both alpha and beta particles at different times. If you put that sample in a lead block and then you drill a hole in the lead block to allow just a beam of that radiation out, and then you focus that beam even more by passing it through another filter of some sort, and you get a very fine beam of radiation. Um, you have a beam of radiation, and you can manipulate that beam. And so, what they did in this experiment is they actually put magnetically charged plates, the positive one on the top, the negative one on the bottom, on either side of this beam of radiation. And then they charged these things. And what they found is that there were three different signals. So without the plates being on, all of the radiation landed here. But when the plates were turned on, they saw things still landing in the middle. They saw some things landing way up here, and then they saw some things landing down here. And so that told them, first of all, it told them that there were three different kind of particles or energies that were being emitted. It told them that and it told them that those energies or particles had different charges. So the thing in the middle that was unswayed by the positive or the negative plate, that told them that that thing had a neutral charge, right? Because what we know is that opposites attract, so positives attract negatives, but if something has no charge, then it's not going to be attracted to something with a charge, and so those things that were not attracted to anything have no charge. They are neutral, and those were the gamma rays. The things that were pulled upwards or deflected towards the positive plate must have had, in that case, a negative charge, right? Because the negative would be attracted to the positive. So they're like, oh, these things up here, these are our negative particles. And eventually we started to call those things beta particles. And the things that were attracted towards the positive plate or deflected in this direction, sorry, the negative plate, those things we knew must have a positive charge because they were attracted to the negative plate. And eventually we started calling those the alpha particles. Now, another really important thing to note here is that they also traveled different distances, right? The beta particles traveled a lot further away from the middle than the alpha particles, which told us something about the mass. It told us that the negative particles must have quite a bit less mass because when exposed to the same amount of force, these magnetically charged plates were the same amount of magnetized, just one positive, one negative. When exposed to the same amount of force, the beta particles were moved more and the alpha particles were moved less. So we knew, okay, the beta particles are less massive because they were able to be moved more by the same amount of force. The alpha particles are more massive because they moved less when exposed to the same amount of force. And in fact, from this, and depending on the amount of energy on the plates and the amount of distance covered by these things, they were actually able to calculate and predict pretty closely what the masses of these things were. So, a very, very simple experimental setup that yielded a lot of information and a lot of very useful material. So, if you were curious at all about how we discovered these things, there's a little bit of background for you. Now, here's another question you might have. And again, I just want to reiterate that this is the optional part of the video, right? I'm not going to test you on that last slide or this slide or the next slide, but this is for any of you who are interested in knowing a little bit more. Um, it is not random what kind of decay happens. So this slide is intended to just kind of break down that misconception. I'm not saying that, well, something's unstable and we don't know whether it's going to go through alpha decay or beta decay or release gamma rays. There is a pattern to it, right? And what this graph is showing, and it's the same graph in two different versions. So let's focus on the one on the left because I'm not in front of it. What this is showing is a ratio of protons to neutrons in the nucleus. And what you can see is that um, decay is going to happen kind of depending on the ratio. So the black line in the middle is showing stable nuclei. If you get the right ratio of protons and neutrons, then that nucleus is going to be stable and it's not going to be an issue. But if you're imbalanced in one direction or the other, it's going to result in decay. And it's pretty easy to see what kind of decay is going to happen, right? If you have more protons than neutrons, so if you kind of fall below this black line, you're going to go through the orange or the red or the yellow type of decay, which is like beta decay or proton decay. There are quite a few types of decay that we are not talking about. Um, but if you have more neutrons than protons, if you're more towards the left of the black line, right, you're going to go through this like blue type of decay, which is a different kind of decay. So this is all just to say that it depends on the ratio of protons and neutrons in the nucleus that determines if something is unstable and what kind of unstable it is. It is predictable what kind of decay something is going to go through. And to take that one step further, it's also really important to note that things often decay multiple times. So just because something is radioactive and unstable and it decays into something else and it goes through, alpha or beta decay or whatever it is, doesn't mean that the new thing that it becomes is going to be stable. In fact, oftentimes, something that's unstable decays into something else that is also unstable, which means that that is going to decay into something else, which could also be unstable, which is going to decay into something else, which could also be unstable. And so, for a lot of these really large radioactive elements, there's something called a decay chain, meaning that there's a predictable pathway, again, predictable because of what I showed you on the last slide. There's a predictable pathway of what decays this thing is going to go through. For example, uranium 238, it's going to decay into thorium 234 and then into polonium, I believe 234, and then into uranium 234. So it goes back to uranium, but a different isotope of uranium. And then it decays into thorium. Again, it decays into thorium, but a different isotope of thorium. And then radon, and then radium, sorry, and then radon, and then polonium, et cetera, et cetera, et cetera. And eventually it gets down to lead 206. And lead 206 is a stable isotope. All right. So things often decay multiple times. And the last thing I want to say is that radiation is not always a terrible thing. We often focus on the bad, focus on the potential for radiation to cause harm to us or change our DNA or mutate us or make us into the Hulk or whatever it is. But radiation is also an extremely important part of our medical practice, right? Being able to take images like x-rays and CAT scans and that sort of thing. A lot of that is radiation based. And if we didn't have an understanding of and a usage of radiation, and if it didn't exist, we wouldn't be able to get accurate information about what's going on inside of people's bodies in order to treat them well. We also use radiation and radiometric dating to discover things about the Earth previously. It's how we date fossils and rocks and ancient samples of stuff that we don't know how old it is. We use radiation as a tool to figure out how old that stuff is. Even there's some crazy examples of how radiation is used, like it can be used to find counterfeit paintings. Because when we started making and setting off atomic bombs, we actually, this is kind of crazy to think about, but we permanently changed the structure of our atmosphere and our world. We introduced new elements to Earth that had never existed on Earth before by setting off atomic bombs. And those, isotopes that we created kind of landed on Earth and they soaked into crops and they're attracted to, well, I shouldn't say that. But basically, they've ended up like in crops and they've ended up in the crops used to make the pigments used in paints, which means that paintings done after 1945, I think it is, paintings done after the detonation of the first atomic bomb contain trace elements of these isotopes that did not exist on Earth before, whereas paintings before that time do not contain those isotopes. And so you can actually tell whether something is a modern fake of an ancient painting, not ancient, old painting, by testing for these rare types of isotopes. And if they're there, you know it's a fake because you know it was painted with paints that contain those elements that were done after a certain point in time. If it doesn't contain those elements, then you probably say, oh, yeah, it's probably an original because it was done with paints that didn't include those. So it must have been done, before that time. Unless the counterfeiter is really good and has really good resources and can get their hands on paints that were made before 1945, which I imagine are super rare and hard to come by. Not saying it's impossible. But anyway, crazy stuff. Radiation can be used for human benefit. And that is a very, very long video. I hope that it was interesting, informative, helpful, something. And I look forward to seeing you guys in the next video. Take care, everybody.